Okay, so the chain rule. Now, the chain rule refers to us differentiating a specific type of function, and those types of functions that we're going to be differentiating are composite functions, or in other words, a chain of functions. So it's basically applying two things to a number, or to a result. So an example of a composite function to remind ourselves, let's say we have y is equal to the square root of 25 minus x squared. Now, we know this as the as a semicircle with radius 5. Okay, so the top half of a semicircle with radius 5. And we learned in the previous lesson a way to actually differentiate this. Now, when we differentiate something like that, what we can do is, well, what we were given was just the result it turns into. However, this chain rule is actually going to help us differentiate that on any type of function in the same way. So, remembering that if we were to put a number into this, okay, two things are being applied. So let's start with a number. So let's make, say, x is equal to 0. Okay, then 25 minus x squared would be equal to 25. And then y is equal then to 5, which is the square root of 25. So like we're doing sort of 3 steps. So we're doing the inside first, and then we're square rooting it, okay? So the idea behind this is that we're going to effectively make a composition, a decomposition of the original function, so the y is equal to 25 minus x squared, and we're going to express it as essentially one function by doing a substitution. So what we're going to do in this case is we're going to let u be equal to 25 minus x squared. Okay, and so when we do this, we can then rewrite y as the square root of u. So we've got two different functions now, okay? We've got a y that's made up of u's, and we've got a u that's made up in x's, okay? So what the chain rule says is that, well, if we've got, our derivative, if we're trying to find our derivative, dy dx, and remember that this is the limit as delta x approaches 0 for delta y over delta x. So that's the definition of this. Okay, we can rewrite this as the limit as delta x approaches 0 of delta y over delta u. So the derivative of this times the derivative of this, so delta u over delta x, okay? And because differentiation, or finding the derivative of two products is, I want to say commutative. I always forget which one's which. It's either associative or commutative. I think commutative is the one I want in this case, as in I can separate these to be the limit as delta x approaches 0 of delta y over delta x times the limit as delta x, that should be delta y over delta u, not delta x, times the limit as delta x approaches 0 of du dx, or delta u delta x, okay? And so we effectively get dy, that should be d, not delta, so we get dy du times du dx, okay? And this is actually going to help us differentiate these functions. Basically, what we're saying is take the derivative of this and multiply it by the derivative of this. So using this example, okay, where u is equal to 25 minus x squared, okay, then du, so differentiating u with respect to x, in this case, was going to give us, well, the constant term disappears, and minus x squared is going to become minus 2x, okay? So that's du dx, and now for dy du, okay, so if y is equal to the square root of u, okay, which is the same as u to the power of a half, okay, then dy dx is, or dy dx is going to turn into so the half comes down the front, and we're going to get u to the power of a negative half if we subtract 1 across, which is the same as a half times 1 over, 1 over the square root of u, okay? So that just becomes 1 over 2 square root of u. So remembering that our dy dx is going to become dy du times du dx. Okay, so my dy du in this case, and for some reason I've put a x up there again. So it should be, oh no, that's right. Oh god, silly. So our dy du, which is 1 over 2 root u, so 1 over 2 root u, times du dx, which is minus 2x. Okay, so that's going to become, so remember this is over 1, so it's going to be minus 2x over 2u. Okay, the 2's are going to cancel out. I'm going to be left with negative x over u, and we just then need to substitute our u back in. So our u in this case is, the square root of u, not just u, so it's got to be the square root of u. So square root of u, so 25 minus x squared, so it's going to become minus x over the square root of 25 minus x squared, like that. And that's our dy dx. Okay, so you might remember it looks very similar to the results we came across yesterday, okay, where our dy dx of our semicircle functions actually gave us a very similar result, okay? And so we can use that for any composition of functions. It's not just for the square root functions, it's for any. So let's have a look at some examples where they are not square root functions. So in this case, we've got use the chain rule to differentiate each function. Okay, and the first function we've got is y is equal to 3 minus 5x cubed to the power of 7. Now, the shortest way to actually answer these, okay, is to start off by, well, again, I'm just going to write my function out because it's what I do. Okay, and what I'm going to do is I'm going to put u, okay, so we need to make u be equal to something, so we're going to let u be equal to 3 minus 5x cubed, so it's just what's inside before we apply the power of 7. So then du dx, so the derivative of u with respect to this x value here, okay, the 3 is going to disappear, and then, so we're going to be left with the minus. Now the 3 comes down the front, so it's 3 times 15, which is 3 times 5, which is 15, then x squared because we subtract that. So derivative of u is that, and then so y is going to be u to the power of 7, okay, because we're replacing that. So dy du is equal to 7u. Okay, so therefore dy dx is equal to dy du times du dx. Okay, so we're going to put our dy du, which is 7u, times du dx, which is minus 15x squared. Okay, so we're going to start off by doing our putting it all together. So 7 times minus 15 is equal to negative 105. So it's negative 105 x squared u, and our u in this case, and there should be a 6 up here too because I forgot to put the 6 there. Jeez, this is what happens when you're out of practice with your derivatives. Okay, so it should be a 6 up there. So then when I substitute my u back in, so remember u is equal to 3 minus 5x. Okay, so I'm going to put my bracket in, and it's going to be 3 minus 5x to the power of 3, and that's going to be to the power of 6 like that. And that's our derivative of 3 minus 5x cubed all to the power of 7. So you could expand that all out. Expanding it all out takes forever though. This is a way to actually work this one out without having to do all the other unnecessary stuff. Okay. So let's do b then, and it's going to be pretty similar. So in this case, b is equal to, I'm going to say, so y is equal to 4 lots of 2x plus 7 to the power of 4. Okay, so what we're going to do is we're going to let u be equal to 4, sorry, not that. We're going to let u be equal to the inside. So it's going to be 2x plus 7, okay? And so that means that y is going to be 4 lots of u to the power of 4. So dy du is going to be equal to 16u to the power of 3, and du dx, okay, is going to be equal to 2, okay? So then our can't find it. So then our dy dx is equal to dy du times du dx. Okay, so dy du is equal to 16u cubed times 2. So it's the same as 32u cubed. Okay, and then we're going to put our u back in, so it's 32. So I should write dy dx is equal to 32. Now our u is 2x plus 7, so we put that back in, 2x plus 7, all cubed like that. Okay, so it's a little bit of work to do it, but basically you just need to make the appropriate substitution. So your substitution is basically going to be whatever's inside the brackets, whatever's underneath the square root, something along those lines. But once you do that substitution, everything should work out fine, and you're going to get the derivative that way. Okay, so very complicated curves, but give us really, it's finding derivatives not too hard. Okay, so with that being said, I'm going to leave that first video there. So that's finding the derivative. What we're going to do next is we're going to have a look at the standard form for whenever we've got a linear function inside. Okay, so basically there's going to be a really sort of shortcut way to do it.